Hi there. Welcome back to our continued study on limits. And so far, after watching a couple of my lectures about how to find limit, so far anyone viewing and follow along with my videos have noticed that finding limits so far has only been based on either using a table to eventually estimate your limit or using a graphical approach. So graphical approach has a disadvantage because we don't know all graphs out there. I mean, we don't know the graph of all function of every single function. We only know the graphs of a few basic functions. We don't know if we stay with the table approach, then a lot of time it's gonna be really every single time we have to break it down to a left table and a right table, and that takes a lot of time and effort. So at this point, learning through our lectures, a couple earlier lectures, then anyone viewing and following along my video lessons is going to start motivating yourself into hunting for a new method, some kind of method that's going to be, making it the finding limit process a lot more effectively. We need a much more efficient method rather than just hopelessly construct tables and graphs, even though those ideas will always work. But so in that way of how we search for a better and a more effective method to work with finding limits, then here I'm going to start introducing for you the limit laws. So here we're continuing to work with limits, but now allow me to introduce the limit laws. And so as I introduce the laws, anyone viewing the video lesson here, make sure you are going to take notes. And I'm going to be switching back and forth between my two boards here because I'm going to be writing the laws here, and then I'll be doing some illustration examples on the other board. And then at the end, after we have shown all the laws here, all the limit laws, then we're going to do some combined example. So that's the plan for this particular video lecture. All right, so now to start out with our first stepping stone here, let's look at limit laws number 1. And my real aim here is that eventually one day when you are all fluent with these laws, you don't need to refer to these as law number 1 or limit law number 2. Every author of the textbook has his or her own way of organizing these laws, whichever that's suitable for your learning. So I put these laws in my own order here in this lecture, only once again in my coming out from my own experience that I feel it helps my students to learn these laws as they learn through their calculus journey. All right, so limit law number 1 right here. As far as naming, I would call that it's the sum. And actually, before I write down limit law, all of these limit laws we're about to learn based on, how about I'm going to say let the limit of our function f of x as x comes to a given limit point to be a known value, a known and finite value L. And let's say our limit of g of x function as x comes to the same limit. So these two functions f and g are a given function, and we are given specifically limit point A. And now, so what's given here further is that as x getting close to a for this function f of x, then the function f of x itself comes to a finite known limit L. And as the function g, as we're letting x getting closer to a as we're letting x getting closer to a, then our function g also has a known limit. Let's say a finite number k right here. Okay, and so before I starting writing down the laws, these are given information. So law number 1 now, and we are about to write it down. So law number 1 is saying, as far as the name, the sum and the difference sums and difference law, or sums and difference rule. So the idea now is that sometimes our function comes out from two functions, f of x and g of x, being added together as a sum. And we are asked in our problem to find the limits as we're allowing x getting close to our given limit point A in particular. And so this law number 1 here, so here, because it's a sum adding two separate functions here, this rule here, this law we're currently learning, that's why it's being referred to as the sum rule or the sum law. So it allows, the sum law now allows us to first find the individual limits. So the individual limits of our function f of x, which is already a known value. And then we are going to add that to the individual limits on our function g, which was also a given known value, as we were letting x getting close to A. And then as I move on throughout all the laws here, then you can see that I'm purposely pointing things to the kind of limits where we're letting x getting close to A generally from both sides. And then eventually I'm going to make a couple of remarks later on. But so here it goes. That's our first rule, and I call that the sum rule or the sum law. And I'm only about halfway finished with this rule. But now allow me to navigate over to the other board, and let's do a quick illustrating example. All right, so as an illustration example right here, the sum rule that we're currently learning is particularly useful when we have something like this. And I'm not even going to name my example number as example 1 or 2 or whatsoever. Those are going to be saved for the actual formal examples where we apply all the rules we've learned together after we've learned all the laws here. But say, if we're looking at something like find limit of the function x plus 3, okay, and at a given value x is coming to about 1. So the point now is that we don't want to build a left-hand side, an LHS table and an RHS table. We want to completely bypass any of those table approach. So the rule here, what we just learned, the rule allowed us to, and what I recognize here is that this function comes out from, it's the addition or it's a sum of two separate terms. So you can, anyone arriving at a calculus course here should be well aware that a sum of two separate terms here is, each of the term here is nothing but just another function. So how I see that now is that according to the sum law that we've learned, we are allowed it to break it down to one function, one simple function, x right here. So this is f of x equals x. And remind yourself, we have seen this limits before. As we're letting x getting close to 1. And then the sum law allowed me to add with the other individual limits for the constant 3. So the constant 3 in the beginning function was a term, but in another way of seeing, it's a one function, a constant function on its own. So now we're letting limits getting close to 1 generally from both sides. So we have already learned throughout the special limits, and we have proven this through table. Limit of this simple function x, when x getting close to 1, is simply 1. So now this limit is known to be 1. So it looks like we're plugging 1 into the function, but we're actually not. It was a well-proven process that we've done, and we put that somewhere into our pockets reference. And as we're moving on to the next term, this function is a constant function. So regardless of wherever the limit points that we're approaching, the function value remains, or approaching to that limit, which remains the same as the constant. So in the end, we're having now two known limits. Now we can, the sum rule said, or the sum law of the limit says, we can add up these two known limits, and our final limit here is going to be 4. So now, ladies and gentlemen, I'm now telling you officially that the limit of this function x plus 3, we completely bypassed using table. And this function here, we are in this problem we're allowing x getting close to 1 generally from both sides. We found our final limit of this function is to be 4, and it's a completely legal work for us here. All right, so now the sum, basically now you've just seen through the example. So a sum basically is indicating that we got two terms being added. So now, similarly, if the two functions f and g, instead of being added together, they could have been, there are other times where the functions f and g are being related by a subtraction or by a subtraction relationship like this. So there are times where there's a minus operation between f and g, or here I'm saying that if we're taking limits on the difference of f minus g, then the difference now, instead of looking at the sum law, we're now switching our attention to looking at the difference law, the other half. And so a lot of time when I'm teaching, I usually see sum and difference as one rule over here. But so back to the rule here, the difference rule allows me to break this limit into two separate ones. First, you find your separate limits on the function f of x, and you're going to have a known limit L. Then you're going to find your separate limits for g of x, and you're going to have supposedly some known limit k. Then our final work here is simply just subtracting out the two limits. And again, let me do another demonstrating example. So back on my board, as another illustrating example. This time we're looking at, let's say, we're trying to find a limit. Our function has two terms, but x minus 10 actually. And we would like to find a limit of this function having two terms, as we were letting x coming close to, how about 2? Okay, and so the difference law. And the reason I mentioned the difference law now is because right here in our problem we have two terms, but the only two terms we have in our current function, x minus 10, is a difference between the two terms. And so limit law that we just now learned allowed us to separate it out into one individual limit for x, as we were allowing x get into 2. And then whatever we know for those limits, we are going to subtract the limits of the other function, which remains as a constant function, which appears to be a constant function. And once again, we're letting x coming close to limit point value 2. And so once again, we already learned through our special limit that this limit is going to be 2. So it looked like I substituted the value into the function, but really it's not. And then I am going to subtract 10 because limits, regardless of whichever limit point, but when we're finding limit on a constant function, the limit turns out the same as the constant function. And so here 2 minus 10 equals minus 8. We have for ourselves another limit problem that we can solve. So the technique to apply the limit laws here using the sum and the difference rule already unlocked a lot of problem for us. But instead of bringing up like more challenging examples, allow me to wait until we've all seen through all the little elementary laws, and then I'm going to bring it in, and I'm going to apply that into a couple examples where we're going to apply all of that skills we've learned. All right, so now back into my board here. Let's get ready for law number 2. So law number 2 says about a lot of times you have a function and the function appears to have a constant multiple. Let's say so c, a constant c times f of x, and we are asked to find the limit of this overall function c times f of x by letting x approach some given limit point a. All right, and so due to this nature of the function, it has a constant multiple multiplied to a function. So we refer to this law as the law about constant multiple. Okay, but so now back to the way how we handle, back to the law itself right here. This law allows us to simply, you only need to find the limit individually for the function itself, which will give you your known limit previously. And once you know what that limit is, you simply just need to multiply with that constant multiple c. And that's how it allows us to find the final limit. So again, let me show another example here to demonstrate the idea. But how about, let's say we want to find limits of the function 10x. So 10x is our current function right now. Let's say we want to find a limit of 10x as we're letting x getting close to, how about -3? Okay, and so what I realized about this function 10x is that 10x allowed me to do a little bit of tearing it down work right here. This is just scratch work and how I recognize my work right here, but 10 is a constant multiple. And x here is some function we will know how to find limit easily. So 10 times x. And so now constant rule we've just now learned and seen in the other board now allows me, that constant rule right there, that constant multiple rule allows me to find the limits. I need to have a little more space for myself, but find the limit of the simple function x by letting x getting close to -3, generally from both sides. Then whichever comes out of this limit, we can just simply multiply with that constant multiple, and which is making the process a lot easier. And so in that way, I'm going to erase all these unnecessary explanation at this point. So we already learned through the special limits that this limit here is going to be a -3. But now with that known -3 as a final limit is to be multiplied with 10, our final limit here is going to be -30. And we now have another answer to our limit problem. Okay. Now let's get ready for our next rule, next law right here. So for our next law, and I'm going to call that according to the order of how I put my laws here, and this is law number 3 right here. And we're looking at, how about, I'm going to name that product of limits. Okay, and I'm trying my best to avoid the term product rule, and you will know the reason why later on in our learning. But for now, I call it's a law, it's a rule as well, but I named this thing the product of limits. So it's the law about products of limits. So, but the idea is, once again, the idea here is this. Now we have a function f, and our being in a product with our function g. So our main function is being a product of f and g, and we are asked to find the limits of the overall main function. So you can see that according to order of operation, we are finding the limit of the product, limits of a product f times g, and then once again at some given limit point. So this law about product of limits right here allows me to find the individual limits on f of x as one separate one. Of course, as x getting close to a, and whichever that is, that value is, we are going to multiply with the limits, the other individual separate limit for g of x, as we're letting x getting close to a. And so, again, allow me to bring up another example over here. And in my example, let's look at, how about, let's find the limit of a product 2x times x minus 3. Okay, so what I have here is a product 2x can be regarded as one function, and in products with x minus 3. and then let's say we can choose a limit point. How about going to 1? Okay, and so the product rule now, I mean I just said it again, I mean, even though I'm trying my best to avoid that name, but here the products of limits, this law allows me to first, I only need to worry about finding separately the limit of this function, limit of 2x, when we're letting x getting close to 1. And once we got it done, we can multiply with the other separate limits as a separate limit. The limit on the function x minus 3 as we were letting x getting close to 1. So now we're gonna, the product of limits law allowed us to separate it down into 2 separate little individual works. And then so now we have seen how to work with similar problem like this. It's a constant multiple in this first limit. So now that allows, it is nothing but just a 2 times the limit of the function x, that simple function, where we already had an answer for. And then this thing here allow me to open another set of brackets. And then here what I'm having 2 terms and being connected by the minus sign, the difference. So the difference rule again apply here. And you can see that you can already start applying those rules we have learned earlier, those laws we have learned earlier. So here we're looking at limit of x, that's x getting close to 1, minus limit of 3, that's x getting close to 1. So in this way over here, the first, I'm starting to run out of space quickly, but the first limit here is a 1. So we have looking at 2 times 1. And then inside of my bracket here, and I don't think I need square bracket, it's a pair of parentheses is perfectly good, but I'm looking at 1 minus 3 according to the law we have learned. Actually, I should have used a bracket here. Okay, so far things are starting to look like substituting values in, because these places right here, they're indicating those are just exactly our limit point being substituted into the function. But be careful about that thought of yours right there. I would like you to understand this as the entire process of how I apply the different laws of limits into the work, instead of simply jump boom from the first step into substituting the value here. That's going to be way misleading for whoever reading your work, and eventually it's going to lead you to dangerous understanding as well. So keep in mind, it works similarly, and that's the whole point of all these limit laws, is make things to work almost like substituting values in, but they're in the end they're still not. It's all because we already approved that limit of x as x coming to any limit point is already known. So we already know, we nailed that down to be among one of our special limits. And then the limit on any constant function, we also knew that already. And so now back to this problem, final limit must be, so that's a 2 times a negative 2. So our answer here is negative 4, and that's our final limit for this problem. All right, and so, all right, and now back to my first board here. Let's now look at law number 4 here. So here also I'm trying my best to avoid the name the quotient rule, but instead I'm calling this is the quotient, the law's name. It's the quotient of limits. Okay. And so the idea again, instead of having a product, a lot of time we're asked to find the limit at x getting close to a limit point A on a function where it comes from as a quotient of f of x divided by g of x. So our main function that we're considering the limit is a quotient of 2 other functions, so f and g. And so this quotient of limits right here allows us to find a separate limit for f of x, which we will know the value easily, and then whichever comes out from that limit, we are going to divide by the similar limit. And what I mean by that is the limit to the same limit point, but on the other function g of x. And so I am going to add some more detail to this rule right now, but that's the biggest part, the biggest core understanding of this quotient of limits rule. So allow me to get on the other board and we're going to see some illustration example. So now let's look at this function. Let's say we are given x over x plus 1 and we are asked to find limit as x is getting close to, you can pick out of your own creativity. How about x getting close to 0? Okay, so this function right at first sight right here is indicating that we're having clearly right in front of anyone viewing this video, it's a quotient. There's your f of x right here being a function, simple function x. In the bottom here, in the denominator here is going to be that function x plus 1. And so the quotient that we just learned, the quotient of limits, that law about the quotient of limits just now we've learned, allowed me to take that quotient into two separate ones. So now I'm going to find one separate limit as x coming close to 0 for the function x. And I am going to find another separate limit on that function x plus 1. As I'm letting x getting close to 0. The one in the numerator here is easy to handle, but the one in the denominator is currently the answer. The one at the denominator currently is not too obvious to see the answer, but what I can see, I can apply the sum rule one more time to tear it down into two separate limits. So one limit for the function x as x getting close to 0, and plus another limit for the constant function 1 as x getting close to 0. So in the end, it seems like so far throughout all of these examples, the illustration examples, and it's all about we have to try to find our way to break it down to eventually it contains those two elementary special limits. Limit of the simple function x as x coming close to your given that limit point, or limit on a constant function. And in the numerator, of course, limit as x getting close to 0. So now feel free to start substituting values in, because now substitute, I mean we substitute value of a limit. So this entire limit here is a 0, 0 on the numerator. And then this entire limit in the first term of my denominator here is 0. It's starting to be a little threatening for somebody viewing this, but don't worry, it's actually 0 plus 1 in the denominator. So we don't have to worry about dividing by 0. We're still going to have, so we have a 0 over 1, which is equals 0. Okay, and so here's the way how we handled a limit problem. We completely bypassed. We bypassed using tables, and we were able to find the limits a lot more effectively. But so what was that other detail about this law that's still waiting for me to put in? Now, in the end here in this problem, once we work through the limits, notice we have to divide. And it is known for human being on earth that we cannot divide by a 0. So we can only proceed with this law anytime our limit is non-zero. So make sure that you got to check that this limits in the denominator have to be a non-zero limit. So provided that rule is only applicable provided that limit of g of x, whichever one comes out in the denominator, must be, limits coming close to a, must be a non-zero value. It's a pretty critical requirement. So let me quickly switch into the other board there. And the reason I could proceed completely all the way to the end was because at the end my overall limit in the denominator did not turn into a 0. It was a 1. It was a non-zero value. So my overall value was a 0 here. So 0 divided by 0, it's completely okay. I mean 0 divided by 1 is completely okay. It gives us an answer of 0 here at the end. All right, so we are now ready for law number 5. And so with law number 5 right here, I'm going to name that it's the power. I'm trying my best again to avoid using the name power rule, and you will see my reason for as we've learned through later on in the quarter in our learning together. But here I'm going to call that it's the power of a limit. This is how I name that law right there. It's the power of a limit. Okay, and so let's say we are asked to compute, to evaluate the limits of a function f of x, but the function itself is being raised to a power n here. And then we're finding the limit as we're allowing x, the main variable of our function, is to approach a given point a given limit point a. Okay, and so this law, the power law of a limit right here, allows me to find just the individual limits of f of x. So limits individually for f of x as x getting close to a. Once we know this limit, we can just simply take that limit raised to the nth power. Okay, and there won't be any special details need to be added to this limit. So we are now ready for seeing some illustration example. Okay, so for that new law right here, law number 5 here, let me come up with some examples, some quick example. Let's say x to the 5th, and let's look at x coming to 2. So x to the 5th is a function, is our function, but the way how I'm seeing this is we already had a known function being x, and this function is being raised to the 5th power. The 5th power. So that's how I'm seeing it. So you can treat our function f of x here as just simply the function x right here, and then f of x is being raised to a power, so n is 5 in this case. All right, so in that way, here's how we apply the power of a limit law right here. So with that law now, we're allowed it to find just the separate limits for x, which is quite simple, as we're letting x get close to 2. Then whichever comes out of that, of this limits, which we will know quickly, we are simply just going to raise that limit to the 5th power. And so now in that way, here's how I'm seeing it. This special limit, everybody knows by heart, it's going to give you a value 2. And so it looks like, so now once again, I have to remind everybody, because things can get dangerous easily, but it looks almost like we're substituting the value 2 into the function, but we're not. It's all because it was all due to this previously proven limit of x, of the simple function x, when x getting close to 2 gives us a 2. Then once we know that limit, we can go ahead, according to limit law number 5, we can go ahead and raise that to the designated given power. And so here's how it's given. So at the end, 2 to the 5th power is 32, and now that is legally our final answer for this limit. All right, and last but not least, our 6th law right here on the list. So the law here, I'm saying, how about let's call that the root, okay, of a limit. Okay. So there will also be a lot of times that we are asked to find the limit of a function, where our function comes in a form that we're looking at some nth root of a function f of x. So overall, this is one function. It's the nth root function, and whichever expression inside of the nth root, it can be regarded as another function. And then we're asked to find a limit as we're letting x getting close to a. And so this law right here, as the name is stating it, root of a limit. So that law allows us to, the law we're about to learn here, now it allows us to find, hey, let's just only worry about the individual limit inside of the root. Inside of the root. So inside of the root, there's that function f of x. So let's only worry about that function and find its limits as x getting close to a. If that limit exists, we are going to take that limit's value, raise it to the nth power I mean the nth root. And that's how we find the final limits. And so this particular law, once again, allow me to switch to the other board to do a quick example, a quick demonstration example. But so, if you look back into all of your algebra courses that you've learned, see, square root function is a quite famous function. So let's find a limit. But how about I'm going to start purposely, play tricky a little bit. How about square root of x minus 3. Okay, and then let's find this. Let's find its limits as we're allowing x to get close to, let's say, 4. Okay, and so what I see here, the way how I see it, there's an f of x function. So this part inside the root, inside here it's a square root, but generally as a generality, I want everybody to understand this as we got a function f of x. This is f of x, okay, and being inside of the root, inside the square root, okay. And so the root of limits law that we've just now learned allows me to find a separate limit on x minus 3. And once we can find that limit successfully by letting x coming close to 4, then we are allowed to take the final square root on whichever value this limit turns out. But then it takes a little further step to find this limit. So inside the square root, it looks like we have to move on one more step. We need to find a separate limit for x. Then we subtract that separate limits for the constant function term 3. Both limits came to 4 as the limit point, generally from both sides. And each one of these now is easy to find an answer. And so what we're looking at now is a square root of 4. So it looks like 4 is substituted in for x, but it's not. It's just we have to go through, a really lengthy process. And then minus 3. And this is going to be square root of 1. And our final answer here is 1. All right, and so now we are ready for our first example. So in this time, for any formal example over here, any of the example I'm about to show now is about how we apply all of the rules. So we've had 6 limit laws here. A lot of textbooks break it down into though surprisingly, many textbooks break it down into 8 or 9 laws, but I only need to show you generally there are just 6 laws. Law number 1 was a combination of the sum and the difference law, but then all the later ones, they have their own individual ones. And now we are going to apply all of those laws together in each of these example problems. So let's look at example 1. So let's evaluate. Okay, in question A, let's say we have function 2x cubed minus 3x squared plus x minus 5. The function we have here, with this function we are asked to find the limits as x is getting close to, how about 1? Okay, there are just simply a lot going on in this function. It has 4 terms, there are powers, there are constant multiples, and then there are the sums and differences. Okay, a lot going on in this problem, and trust me, if anyone is asking me, even though I've had years of experience working with limits, I don't want to use table to approach and something like this. And so let's use the limit laws and apply all the laws we have learned, and then you will see how valuable of those laws that we've learned. So first of all, this function got 4 terms. It's a mix of difference rule and sum rule. So the sum and difference law allowed me to find 1 separate limit on the function 2x cubed, and then 1 separate limit on 3x squared, and 1 separate limit on the function x, and 1 separate limit on the function 5, Okay, and according to the order of operation, according to the operations here, we have subtraction right there, we have adding here, and we have subtraction there again. And these limits are all getting x close to 1, x getting close to 1, and so on and so on. All x getting close to 1. Okay, so the answer to the two very ending ones right here are quite trivial at this point. So I'm going to hold it on. I'm going to hold it off right there for a couple steps. But let's look at the first two limits right here. The first two limits, we need to apply further rules. We need to apply other laws into being able to tear this down into an actual limit. So what I see here is there's a constant multiple. There's a constant multiple. Okay, so that's just that within that first term, that first limit, we can further apply the constant multiple law right here. So the law says we can just simply keep that constant multiple to separate and only find the individual limits for x cubed. And whichever that turns out to be, we will multiply with 2. And let that come to, so for a guarantee of the, for clear understanding and kind of going with order of operation, we got to find that limit, and then that limit will be multiplied with 2. Then the next one is the same. Subtraction remains there. I'm going to keep 3 as a constant multiple. My responsibility here is to be able to find out what the limit of that function x squared is going to turn out. And x going to 1. Then for my last two terms, as I said earlier, I am going to leave them unchanged for now. I'm going to hold on to them because the answer can come out quite easily. All right, and so now in my other board. All right, so continuing with the steps here. So first term now would become, so first term I have to apply the law, the power of a limit, that law right here. Same here, the power of a limit needs to be applied here. So in my next step, this is what I'm going to be doing. So 2, I am going to multiply with whichever limit of x. When x getting close to 1, I am going to raise that to the third power. That's how things happen. And then I'm going to subtract 3 times whichever happens to limit of x as x is getting close to 1. We're going to raise that to power 2 according to the limit laws. And then we're going to find a limit of x as x getting close to 1 and subtract limit of constant 5 as x is getting close to 1. Now the answer is really clear. Thus, from the inside out, this limit of x when x getting close to 1 is a 1. But then the limit law, power of limit, says that we can raise that to the third power. And after that, we can multiply that with 2. So now only at this step, if you skip all of these steps and jump directly from here, from the first step down to this, it might look like a direct substituting work in, but we're not really substituting values in. Minus 3, 1 square times 1 square plus this limit here is 1 and minus 5. And so now we are ready for final calculation. Our final answer is -5. And that's how we have found it. All right, and same example. Let's look at question B right here. How about x squared plus 1 divided by quotient. So divided by, how about 2x minus 1. And here we're looking at limit as x is getting close to 0. All right, and so once again, here I am going to apply quotient of limits right here. So we got 2 separate functions being in a quotient set up like this. So what I'm going to be doing, I'm going to be breaking it down into one separate limits for x squared plus 1. And I am going to consider a separate limit for the denominator, which is the function 2x minus 1. Both of them I'm finding limit as x is getting close to 0. Okay, and then for each of these, in each of these numerator and denominator, they are functions with two terms here. So let's consider from top down right here. But my numerator function had two terms, so I'm going to break it down to one separate term for the x squared function as x is getting close to 0. And I'm going to need to add the sum rule. The sum law right here is applying right there. And then the limit of 1. It's a constant as I'm getting x closer to 0. And then in my denominator here, I'm looking at the limit. My first term here is a 2x function. So limit law says I can use the difference law and tear it down to simply considering the limit on the first term, 2x, by letting x get close to 0, minus limit of 1 by getting x to 0. And further, from the previous step here, then now I can see that I have limits of x, then whichever it turns out, x coming close to 0. I can square that, and then now I'm going to add with limits of 1 by letting x coming close to 0. And then my denominator, I'm going to have constant multiple apply, so I have 2 times the limit of x, by letting x getting close to 0, minus limit of the function 1, by letting x getting close to 0. So all together now I'm ready for values, for different limits, value to be substituted in. So limit of x here, this is 0. Square plus, this gives me a 1. That gives me a 2 times 0 minus, here is a 1. And so we have be cautious here. We are using the quotient, the law of a quotient right here. And we got to make sure you check right here. But 2 times 0 minus 1 is not going to give us a 0 value in the denominator. Or in other words, this denominator is non-zero. So it's completely safer to advance further into the next step. And so now I'm looking at 0 plus 1 is a 1 divided by negative 1 in the denominator. Our final answer, our legitimate answer now is negative 1. That's the final result right here. Okay, so one more time, let me give everybody anyone viewing this video an overall look of this problem. So we start from the left board, and that's how it turned out. That's how it started out. That was a function. And we work our steps through. And we ended our problem. Yes, it does take a few steps right here, but in the end, we can completely saved ourselves away from table approach. Otherwise, if we stay with table, we're going to have a lot of calculation, and then the prediction for the final value could also turn out hard. So here is our final limit value for this function, x squared plus 1 over the 2x minus 1 in quantity. All right, and now let's get ready for our next one. Question C of our current example right here. How about we have a function square root, and inside of that we have x squared plus 2x minus 1. And here we want to find the limit of this entire function as x is getting closer to 1. Okay, so immediately what caught my attention here is that we have some function being inside of a root. So that reminds us now, and that reminds me about the root of a limit. So we are now at this point of our learning, we are allowed to find individually the limits problem of the function inside the root. That's why I'm now tackling down just that function inside the root, considering that limit as x coming close to 1. And then if that turns out successful, meaning giving us a finite value, then we will be taking a square root. So that means I need to proceed further. I'm now going to leave the square root here kind of hanging out there. I need to proceed with my finding limits of my polynomial here inside of my root here. And so now I can see that I need to tear it down to 3 separate terms. There's limit of x squared, letting x getting close to 1. And then there's a limit of 2x by letting x getting close to 1. And minus limit of 1 as a constant by letting x getting close to 1. So on my other board, and for anyone to be able to review your earlier step, maybe let me put it in this way right here. So let me show the other board as well. But so from that previous step right here, very previous step. So in my current step now, I'm still going to have the square root remains here. The first term of my the first limit inside of my square root, I'm going to need to work a little further. So that turns into limit of x, but then we need to square because the power of the limits law allowed us to do this. X coming close to 1. And plus, now I'm going to look at 2 times the limit of x. And this is according to the constant multiple law right here. And now I'm going to subtract. And here I'm looking at limit of a constant function, which is easily known. And so in my next step, I am going to proceed as so this limit here is easily understood. It's 1, and now that limit is going to get squared. This limit here is 1, but need to be multiplied with 2 and added with the other term. And this overall limit here in my third term inside the square root is going to be 1, and so minus 1. So now my overall limit, we can now go ahead and proceed with the calculation. 1 squared is a 1 plus 2 minus 1. So we're looking at a 0. Actually, I'm lying. Error in my own calculation, but it's a positive 2 for this. So final answer is square root of positive 2.